All right, welcome back. So in this video, we'll define our own queue data structure from scratch instead of using an array. And just like we did with the stack data structure, it's going to be based off of a linked list. So hopefully you made it through the singly linked list section. I'm going to go through this pretty quickly. So if you didn't watch that, if you didn't kind of understand that code, some of this might be confusing. So I recommend you do that first. So we'll have a queue class, a first and a last, and a size property, just like with our stack, and then a node class for each element in the queue that will have a value and a next pointer. So quickly, to refresh your memory on a linked list, what we could do, just like with an array, we have two sort of pairs of options. We can add to the end and remove from the beginning, or we could add to the beginning and remove from the end, right? So we could, for example, if let's do an insert at the very end, insert 80, there we go, and we keep inserting, let's insert again, 54. The first thing that should be removed is the first thing that was inserted in a queue, so that would be over here. So then we would remove from the beginning, just like this. So that's one option. The other option is to switch it and add to the beginning, so we'd insert at the beginning like 99 right there, and then remove from the end, which theoretically would be the first thing added in. Although in this case, because it isn't, because we were doing it backwards. But if we kept inserting, the list would grow, or the stack grows this way. So this should be the first thing added in. And if I remove from there, from the tail, oh no, look at how slow this is. So this is the exact same thing we encountered in the stack video, where in a singly linked list, removing from the very end using pop is slow because we have to iterate over the entire list. Let's do it one more time. Remove from the end, not good. So what we're going to do instead of this is to add to the end and remove from the beginning. So it looks more like this. So our methods are going, instead of push and pop, which is what they are for a stack, the terminology is enqueue and dequeue. So if this is our queue, when we add, I just clicked dequeue accidentally. So you could see it was removed from the beginning. But when we enqueue something, it's added to the end. So it's pushed on. If we're going with a singly linked list, we would call this push. We're adding to the end. And when we dequeue, we're removing from the beginning, which we would call shift. But because it's a queue, we're going with enqueue and dequeue. So this is our idea. It's a singly linked list, or it looks like one, but it has these two methods. So we add to the end to the tail, and we remove from the head. So let's do that now. Here's the classes that we'll go with. I'm going to start by defining those two classes, and then we'll add the two methods. So I made a new snippet, and I'll fast forward through my definition of the node class. All right, so we have node, takes a value in, we set the value to be that value, and then this dot next is null by default. Now I'll quickly define the basic skeleton of the queue class, and it just has a constructor. It takes nothing, and we have a first, which is null, we have a last, which is null, and then a size. And now we just have to add our two simple methods. So we'll have enqueue, which accepts a value, so I'll just call it val. And then we have dequeue, which doesn't. I hate having to type that. I hope oh my gosh, U-E-U-E. There we go. And this should return the first thing that was added in. So this should add something in, and then this will return and remove the first thing that was added in. I'm not very good about, I'm not explaining it in a good way. Anyway, so this will add to the very end of our linked list. This will remove from the beginning. So let's start by enqueuing. So if we look at the pseudocode, our function accepts a value. We've done that. Create a new node using the value passed in. And then if there are no nodes in the queue, set this node to be the first and last property. So that's not all of it, but let's just start by creating the new node. So var new node equals new node with that val that was passed in. Cool. And then we're going to check if there's nothing in the queue. So we could check if size is 0 or if there is no this dot first. In that case, we set this dot first equals new node, this dot last equals new node. So this is our edge case if it's an empty queue. So we set the first and last to be that new node. Otherwise, set the next property on the current last to be the new node, and then move the last pointer to be that new node at the end. So basically add it to the end. So that looks like this, else, and this is identical other than first and last and size. You could replace that with push on our singly linked list. We're adding to the end. We just used head and tail and length. So it's the same logic. So otherwise, this dot last, so the very end, dot next is now equal to new node. And then we just say this dot last equals that new node. So we've moved over that pointer. So we're now looking at the end. And then finally, we're going to increment the size of the queue by 1 and return that. So I'll do return plus plus this dot size. Okay, and then we'll move on to dequeue. And dequeue should remove from the beginning in order to give us the to give us the first thing added in. We're adding to the end, removing from the beginning. So dequeue looks like this. We define the function, it takes no arguments. If there is no first property, just return null. Store the first property in a variable. This is identical to what we did in the stack section, or the stack part of this section. So it's very, very similar. And let's just get going on it, honestly. So dequeue, we're going to start by checking if it's empty. So if there is no this dot first, return null. That means that there's nothing in our queue. Otherwise, we'll make a variable called temp to store the current this dot first. This is what we'll return at the very end. And then we'll just do our exact same logic. So if this dot first is equal to this dot last, we're going to set this dot last equal to null. Otherwise, actually not even otherwise, but just this dot first. So that's our edge case. If there's only one thing left in there, we set the last item to be null. Then we're going to take this dot first at the beginning and update it to be the next item. So whatever used to be there, for example, if this is the current this dot first, we're now going to say this dot first dot next is now this dot first. And then the only other thing we need to do is decrease the size by 1 and return the value of the node. So that's going to be this dot size minus minus, and then return temp dot value. And that should be it. And if we look at this dequeue and compare it to our stack, which it was called pop, but it's the same idea, the code is identical. Did I even use the same variable name, temp? Yeah, it should be exactly the same. And that's correct. That's how it should be. The way that we're implementing our queue, we are removing from the beginning. Same thing we did with our stack. It's just that in our stack, we are also adding to the beginning. In our queue, we're adding to the end. And we called it dequeue instead of pop, enqueue instead of push. Anyway, so let's test this baby out. Let's run our code. I don't know why let's run the code and let's make a queue. I'll just call it new queue like that. And then we'll do an enqueue first. Whoop. What's going on here? It looks like, I have a problem. This dot first, or this dot size needs to be set to 0. So we'll do var queue equals new queue, and then do queue.enqueue first. That looks like it's working. Second and third. And then we'll do a queue.dequeue, which should give me the first thing added in, which is first, and then second, then third, and now it should always give me null. And first and last are set to null, size is back to 0. So I can now enqueue something else like hello, and then I can dequeue hello again, and everything should be happy. And that is our queue. So this queue can grow super large. There's no indexing. There's no problems that we'll encounter. It's constant time for every operation, which is really just adding in and removing. And it is first in, first out. FIFO, FIFO. I don't know what the official pronunciation is. And that is in comparison to a stack, which is LIFO or LIFO, last in, first out. So they're very similar, but also extremely different in how they actually behave. They're similar in the fact that there's two operations, adding and removing. You put something in, you get something out. It's just that the orders are totally different. Okay, so in the next video, I'll wrap everything up, stacks and queues, talk about big O notation, and just summarize it all. Hopefully this makes sense. If you saw the singly linked list section, this is extremely similar. We just put a different wrapper on it, called things a little bit different names, but otherwise it's the same functionality, just slimmed down. All right,